Okay, so this is just going to be a quick tutorial on determining ionic formula and the steps that I use to do that. So I really break it down into 4 steps. The first one is to work out the symbol for each ion. The second is to determine the charge of each ion. And the third is to work out the ratio. And the fourth is to write the symbols with their ratios in the correct chemical conventions, I guess. So we write the formula. Now, when you're doing this, you'll also need to show these steps, some kind of, your thinking in order to get full marks. If you just go straight to writing the formula, then you can't actually show me how you got to that answer, and I can't mark it as correct. Okay, so let's work out what kind of ion compound would we get. So just remember, a compound is more than one atom joined together that are different. So a compound is more than one atom joined together where the atom type is different. Okay, so that's what our compound is, and that's what we're forming here, ionic compounds. Okay, so let's choose some. Let's go magnesium and chlorine. Okay, so when we form ionic compounds, we need something that wants to become positive and something that wants to become negative, and then they will then attract to one another as opposites attract, and then join together and form an ionic compound, or maybe like a crystal or something like that, or a metallic salt. So we can't have a metal and a metal forming an ionic compound, nor can we have a non-metal and a non-metal forming an ionic compound. We need them to be a metal and a non-metal. Okay, so let's write them out. So step 1, what's the symbol? So we've got Mg and we've got Cl. Now, how do we work out their charge? Well, there's 2 ways. We can look at that last shell, called their valence shell, and work out how many electrons they have and whether it's full or not. Okay, if it's not full, they could either gain or lose electrons, and if it's only a little bit full, they're likely to lose those electrons. If they're almost full, they're likely to want to try and gain a few more electrons to fill out that last valence shell. And what we end up getting is a bit of a pattern. So everything in group 1 ends up having 1 electron in their last shell, so they're going to want to donate that away and become a positive ion. In group 2, they have 2 extra electrons and want to become positive 3. Over here in group 3, they want to become plus 3, and that's for the metals. Okay, so the non-metals aren't going to do that, but the metals will do that. And then these ones are going to become plus 4, so the metals in that group. And then we've got the non-metals forming minus 3, minus 2, minus 1, and 0. Now this section between is what we call our transition metals, and they're likely to form ions of plus 2 or plus 3. But any question using those will give you exactly the charge of that particular ion. Okay, so if we look up our group, magnesium charge is going to be plus 2, and chlorine is going to be minus 1. So what that means is magnesium wants to give away 2 electrons, and chlorine only wants to receive 1. So in that given state of a 1-to-1 ratio, magnesium is not being satisfied. It's not giving away all of its electrons, because chlorine only wants 1. So in fact what we need is 2 chlorine ions for every 1 magnesium ion. So we write the ratio as 1 to 2. 2 chlorine for every 1 magnesium, and then we simply write that formula out as Mg GCl2, where the numbers indicating how many of the ion are in subscript. Okay, so that's one done. Let's do another example. Okay, so in this example we've got beryllium and phosphorus. So what ionic compound would that form? So we go across and we go, beryllium would have +2 and phosphorus would have -3. So beryllium wants to give away 2 electrons, phosphorus wants to receive 3. Now you'll notice that that's quite a weird relationship, because how do I satisfy both? If I make another beryllium, then that still is now extra electrons giving away from beryllium and not enough phosphorus receiving. So we've got to find that perfect ratio to satisfy them both. And there's a little sneaky trick that we can use where we basically just swap the numbers that are associated with the charges, and that's our ratio. And we'll have a look at that in a sec. So our ratio would become 3 beryllium to 2. So how does that work? Well, let's look at it. So let's say we have a Be wanting to give 2 electrons away and phosphorus wanting 3. So it needs another one from somewhere else. Well, if it's from another Be, then now we've got a leftover electron. Okay, well let's put another phosphorus. Okay, it wants another 2 now. What's donating that to? Another beryllium. So now we've got each beryllium giving away 2 electrons. Okay, so we've got 1, 2, 1, 2, 1, 2, and then for phosphorus, 1, 2, 3, 1, 2, 3. So they're in that perfect relationship. So then we'd write that out as Be3P2. Now, the thing that I haven't touched on quite yet is once we get to this stage, we need a 5th step, and that is to write out the name of that particular compound. So step 5 would be to write the name if it's not already given. And in this case, what we do is we look at our compound and we go, all right, what's the metal? That always goes first. So in this case, it's beryllium. And what's the non-metal? That goes second. In this case, it's phosphorus. So phosphorus, to indicate that it's now an ionic compound, we replace part of that second non-metal name with the word "ide." So it becomes phosphide. Okay, so if we look at our equation or our chemical formula and it's just a metal and a non-metal, we're going to be ide. Okay, so in this case, it's going to be ide. If it's, say, something like potassium nitrate here, you can see that there's a metal and 2 non-metals. Now that 2 non-metals, because it's got an oxygen in it, we then call it potassium nitrate instead of nitride. So if it was just nitrogen by itself, it'd be potassium nitride. Because it's got the oxygen, we now call it 8. Now, if we know the maximum number of oxygens that nitrate has is 3, if we see one less than that, then we'd use the word ite. But we're probably not going to go into that with our level. Okay, so just to recap. We work out the symbol, determine the charge of each ion, work out the ratio, and then write the formula. One handy little trick is to work out the ratio. We can just swap the number for each charge onto the other side, and that becomes our ratio, and then we add that into our formula. When we're naming them, if it's just a metal and a non-metal, we replace the end of the non-metal's name with ide, so it'd be beryllium phosphide instead of beryllium phosphorus. And if it's a metal and a non-metal plus oxygen, we replace the end of the non-oxygen non-metal with the word 8. So this would be potassium nitrate. So let's just do one more example where we look at working out an ionic formula using one of these polyatomics. Okay, so in this example, we've got our traditional calcium, so a normal metal, but now we've got a polyatomic, poly meaning many, atomic meaning atom, many atom, polyatomic ion. Okay, so many atom ion. If we were to draw that, it would look like this. So we'd have a carbon attached to, we have that carbon attached to 1, 2, 3 oxygen. Okay, and it always looks like that. Okay, we can't suddenly, want to change it to maybe miss one of them. Okay, we can't just get rid of one and call it CO2. This carbonate ion is always CO3. Okay, so we just follow the same steps. We've got our symbols, Ca and CO3. So CO3 is the symbol for carbonate. What's their charge? Well, if we look up on our periodic table, calcium has +2. The carbonates, or any of these polyatomic ions, I will give you their charge in the test or in any sort of time where we're practicing. So in this case, it's actually -2. Okay, so we then work out the ratio. Well, this one wants to give away 2 electrons. This one has a -2 charge, so therefore it's going to become a 1-to-1 ratio. We write it out as CaCO3. What's the name? Well, we notice that it's got a nonmetal plus oxygen, so it's going to be calcium carbonate. Calcium carbonate. Now let's just say the ratio wasn't 1-to-1. Let's say the ratio was 1-to-2. Okay, we'll just make it up. Let's say it was 1-to-2. We can't just write CaCO3 2, because when you actually read that, it looks like we've got calcium plus carbon plus 32 oxygens. So what we have to do is put in parentheses or brackets between our symbol and how many we're saying we've got of that symbol. So in this case, the symbol is CO3, but we're saying we've got 2 lots of them. Okay, so that's how we'd write it if we had needing more of one of our polyatomic ions. We'd put it in parentheses. Hope that helps. You can always go back and watch this over and over and over again, pause, rewind, and ask some questions, and we can follow those up in class. Hope that helped.